So what's a reversible process? Well, there's two definitions we can use. One is we can say it's one where the system and the surroundings are nearly equivalent. So what do we mean nearly equivalent? So we could say that P external is approximately equal to P of the system, or T external is approximately equal to T of the system. And we can go on like this. So let me give you an example of a reversible process. We could have a situation where we have a piston and it's being held down by a pile of sand. Let me just draw the sand like this. Okay, so there's a pile of sand. And the external pressure, not whatever the pressure is out here, we don't care about that. It's the applied pressure. So it's ever being pushed down by the weight of that sand. And the internal pressure, the pressure of the system, is just P. So here we've got pushing down on the piston is P external, which is caused by the weight of that sand, and P is the pressure in the cylinder. Now, the piston's not moving because those two numbers are approximately equal. Now, or they're actually equal. Now, if I flick off one little piece of sand, P external will be a tiny bit lower than P here. And since it's a tiny bit lower up here than here, the piston will move up. And it will move up just a tiny little bit because, of course, as it goes up, this pressure goes down, and pretty soon we're back to pressure external and pressure of the system being the same. So we kick off a grain of sand and the system moves up just a little bit. Great. And we can keep doing this, right? We can just keep on flicking off little bits of sand, and eventually we can go up as high as we want. But the whole time during the process, these two numbers were about the same. They weren't the same, but they were about the same. They differ by, at most, an infinitesimal amount. And we can just show that by saying P external and P, the magnitude of that difference was equal to an infinitesimal amount. It's a tiny little change. Okay? All right, now how is that different from irreversible change? Let's look at an irreversible change. So if a change is irreversible, we could imagine something where we have a piston and it's being held in place by some stops, and then we just pull those stops out. So we've got P and we've got P external, and those things are not approximately equal. They're not equal at all. We pull the pistons out. This piston's just going to fly upward. Okay? And it's obvious that that's a different type of process. But let's look at how it's different. Let's look at how it's different. It's not different only because it's faster. Because we could imagine a process that is very slow, and we could call, there's a name for a process like that. We call it a quasi-static process. So we can imagine having some stops here, and then having a second set of stops, and a third set of stops. And we pull these out, each set one by one. And let's imagine that this distance between the stops was a nanometer. So these are really super thin stoppers. And we pull them out, and then we wait a year. And then we pull the next one out, and we wait a year. And we pull the third one out, and we wait a year. So the piston's going to be moving up by 1 nanometer per year. That's extremely slow. But if this is 10 atmospheres, and this is 1 atmosphere, this is going to be an irreversible process. Because even though it's slow, these two numbers are not approximately equal. Okay, so don't confuse a slow process or a quasi-static process with a reversible process. It has to be the case that we have this, if it were to be reversible, these numbers would be approximately equal. And since they're not, both these processes, whether the piston flies up quickly or we're forcing it to go in slowly, those are both irreversible processes. So if we look at this process, we can also look at it in terms of what would a graph of this process look like? And let's contrast it with the reversible process. So here we've got the reversible process, we've got the irreversible process. So let's look at what happens in terms of a graph if we try to graph molar volume versus pressure for those two processes. So we've got the one where the external pressure and the internal pressure are different, and one where they're approximately equal. So if we graph this one, remember the pressure was relatively high and the molar volume was relatively small, and we slowly increased the pressure, and as we did so, the molar volume increased. And if we did it at constant temperature, we get a nice smooth isotherm. Great. What about here? Well, we started off at a high pressure, low molar volume and went to a low pressure, high molar volume. So that much is the same. But let's think about this for a second. Let's look at that piston for a second. So it's here. We've got some high pressure down here. We've got a low pressure up here. When this piston starts to fly up, and let's draw this a little bit bigger so we can see this a little bit more clearly. So here's our piston. When this piston starts to fly up, the pressure here is going to decrease immediately. But the pressure down here is not, right? We know, let's imagine, just for a point of argument, let's make this 1 atmosphere and let's make this 100 atmospheres. This molecule down here will be surrounded by a high density of molecules. So it's going to have a pressure around 100 atmospheres. But as this piston flies up, it leaves really nothing behind it. So the pressure here is going to drop very, very low, which means there's not one consistent pressure inside the system. In fact, we can't graph it this way. There's no real way to graph it because there's not a single value for pressure, and that's characteristic of irreversible processes, that there's not a single value for some of the variables of the system. So if we tried to graph it, we know that there'd be parts of the system that had a very, very low pressure and parts of the pressure that still had a high pressure, and so it would sort of look like this if we tried to graph it. Okay. And the fundamental difference between these two is that the reversible process we can think of as a succession of near equilibrium states. So the system's almost in equilibrium, it's almost in equilibrium all the way through. And here, that's clearly not so. There's these giant gradients in pressure going through our system when we have an irreversible process. So we can see they're totally different. Now, there's some things about them that are the same, these two classes of processes. Let's imagine that these two dots here, let me circle them with a different color here. This dot and this dot were the same as this dot and this dot. If that were so, then we know that every state function would be, every change in a state function would be the same for both process. We could say that delta V, delta H, delta G, delta S, delta U, those would all be the same if the endpoints are the same, right? Because those things are path dependent. But what would not be the same for these two processes? Well, one thing that would not be the same is anything that's a path function. So Q would not be equal, so Q1 and Q2 would not be equal. And also, work 1 and work 2 would not be necessarily equal because those things are path dependent, okay? And so we really have to be careful because when we're trying to calculate Q or W, we really have to know if we have a reversible process or an irreversible process. So make sure you can make that distinction.